Hi, I'm here to talk about classical probability and some basic concepts of classical probability. And I want to start with this by noting I'm going to use a whiteboard a fair amount this time, which I hope will work out well for us. Um, Classical probability means the likelihood of an occurrence divided by the number of all possible occurrences. What that means is what's the likelihood of something happening, meets some criteria that we have, divided by the number, all the possible ones that are possible in this. The simplest one that comes up is, so you have a regular deck of cards and you want to say, what's the likelihood of the occurrence being a red card out of a normal deck? Well, given there are 52 cards in the deck and half of them, hearts and diamonds, are red, then there are 52 possibilities. And of those 52 possibilities, 26 of them meet the criteria, which is being a red card. So the likelihood probability is 0.5. 26 out of 52 for a red card coming up. That's mathematically, that's the simplest one that comes up. Now I'll give you one that's even simpler than this. I have here in my hand 4 marbles, 3 blue, 1 white. What's the likelihood that I'm going to get a blue marble? Well, given there's 4 choices, there are 4 marbles altogether. What's the probability of blue one? Well, there's 3 blue ones out of 4. So the probability of blue marble is 0.75. What's the probability of a white marble? 1 white marble out of 4 possible. The probability is 0.25. What's the probability of getting a white or a blue marble? It's 1, because that's all the possibilities there are. What's the probability of getting a green marble? The probability is 0, because there are no green marbles in this group. The whole set consists of 4 marbles. I'm doing this, trying to keep it simple here. That's the key piece of this process, is figuring out, well, what's the set? What are the possibilities? Where's the boundaries of this thing, for instance? Some point later, I'm going to ask you, we're going to talk about, for instance, what's the probability of coming up with a Republican voter among all registered voters in Vermont? Well, the set is all registered voters. Understanding what the space or the set is that you're drawing from is a crucial piece of this. And then what are the criteria for a successful or the correct occurrence? In this one, there's 4 possibilities. There's only 4 marbles here. So that's the denominator that we're looking for. And the thing that meets the criteria, whatever it is your numerator. Flip a coin. How many possibilities are there? There's heads or tails. Now, people say, well, it could be on its edge, but it's like it's a very rare occurrence. It's so unusual that I'm going to pull it out. So what's the likelihood of getting a heads? Assuming it's a fair coin, there are 2 possibilities. Heads is one of them. The chances are 1 and 2, 50% that I get a heads. The crucial piece of this is a thing that they talk about figuring out, well, how many things are there possible in this one? And I want to take a little example here that came from my granddaughter, as a matter of fact, that my granddaughter talked to me about the American Girl. If you don't know, you don't have a young daughter of a certain or granddaughter of a certain age, you may not know about the American Girl. American Girl, first of all, it's a marvel of marketing. I give these guys incredible credit. What they essentially try and say to you is, you can order a doll from us and it will be a unique doll. The chances of the girl next door having the same doll as you do are very, very low. Why is that? Because when you order it, you can order any of 5 different face shapes, 3 different skin tones, 16 hairstyles, 7 hair colors, 7 eye colors, and 6 types of glasses. There's more combinations than that, but I'm going to limit to that just to try and keep the job issue fairly clear. So there's all these possibilities. So you might say, my granddaughter comes over to visit and she brings her American Girl doll with her. And the little girl who lives next door says, oh, I've got one too. I'll bring mine over. What's the likelihood that their dolls will be identical? Well, you can actually figure that out here. And part of the way you do is you say, well, how many combinations, how many possibilities are there in this process? What I have here is a little chart that I use for figuring this sort of stuff out, and I would recommend you use it because you will be getting a problem like this about car choices coming up this week. I want to show you how to do this thing. I said there are 5 face shapes, total possibilities 5. Skin tones, there's 3. That makes this number here 15. 5 times 3. How many hairstyles? Well, it's 15 then times 16, which comes out 240. How many hair colors? That's times 7, so you get up to 1,680. How many types of glasses? 6 types of glasses. So your tendency right away is to put a 6 in here, but that's a trap. You're looking at different kinds of girls. Well, there are 6 different kinds of glasses they could have. The 7th option is no glasses. So instead of having, well, your temptation here, because it says 6 types of glasses, to jump a 6 in, there's a 7th here, which is no glasses. So I multiply times 7 here. And now I'm up to 11,760 choices. Let's go to the eye color then. There are 7 eye colors. However, the eyes can be the same or different colors. So what number goes in here? Was it temptation? Well, 7 seems too small. Maybe it's 14. How do we know? Well, let me suggest how you might know here. And this is a place where I want to go back to my whiteboard. One of the things I talk about in here is in the chapter is the use of a decision tree. And a decision tree is basically where you have a choice, and there are 2 choices that come off of it. And from each of that one, there are 3 choices. You go 2, 3, 1, 2, 3. And you just keep, you can say, and off that one, there may be a certain number of choices. So you go off this one here, there might be 3 choices off this. So it'll be like 1, 2, 3. The thing is, I never do a full decision tree. Never, ever, ever do it, unless they're really simple stuff. But I often walk through decision trees because they help me understand what I'm working with. Let me come back here with the eye color. So there are 7 eye colors. Let's say number 7 is blue, and I want to work with that. And this is, if you will, this is the left eye is blue. And over here you have the right eye. With a blue left eye, what are my choices? Well, it could be 1, 2, 3, 4, 5, 6, 7, which is this one by the way here. This means you'd have this option with this option here means you would have two eyes that are blue. For each of these 7 choices for the left eye, there are also 7 choices for the right eye. So the number of choices for eye color is 7 times 7, or 49. See how I got that? And I use a decision tree as a way for me to conceptualize it, to make sense out of it, to think it through, think the problem through, because this stuff can be complex. And the decision tree is a way for me to do that complexity. I don't need to draw out these 7 things for each of these 7 things over here for me to figure it out. But by drawing it up this way, I was like, oh, that's how I get there for this one. So I come back. Come back here and say the number in here is 49, and I multiply that out then, and I get 576, 240 possibilities. So based on that, if I were figuring the probability that the little girl next door, when she brings over her American Girl doll, that would be the identical to my granddaughter's, is 1 in 576, 240. I don't know. I'm not going to do that computation, but it's pretty small. If you have, but that's how that's what this process. This is called the fundamental. I'm showing you here is that what's called the fundamental counting rule. Is how to count up the number of possibilities, and essentially, is you take the number of possibilities and the options on each one, and you just keep multiplying them out. And this little chart, organized it this way, helps make that clearer. I recommend it when you have later in this chapter, you have to do a problem about the number of car possibilities one could have. I'm going to do the same kind of thing for you there. So that's the fundamental counting rule. And it's not hard. The math of it's not hard. It's just trying to think through it's the possibility of thinking through the possibilities and what do they mean. And being clear that even when somebody gives you a number that may not be the right, may not be the number you want to put into your formula ultimately. Glasses is an important one. I have 3 different sets of glasses here. So how many possibilities do we have? Well, we have 4 because one possibility is no glasses. Sometimes options come up like that, and you got to think through what does that mean exactly? The American Girl doll, for instance, I would tell you one of the possibilities is you could have freckles. Well, there's a possibility of freckles or no freckles. And I don't think they give you options within freckles, and it's either they have freckles or they don't have freckles. But freckles with different skin tones is an interesting question for me. I don't know how that would work out. It's just the process. I'm trying to work through the process. How do you think through what they're asking you for here to come up with a denominator ultimately for what are the possibilities that you're working with? Another important concept of this one is, clear my drawing here. Exclusive events versus non-exclusive events. What's the difference between them? Well, I'm gonna draw something here basically to give you a sense of that. You could have an event like this. And I use the thing, for instance, with registered voters in Vermont. You have Republicans and you have Democrats. You can't be both. If I pull somebody, or name at random, out of the pool of registered voters, a person can't be in both these two things. These are exclusive events. On the other hand, you could have and here you might have Republican voters and females. Now, I'm not going to say, don't take what I'm doing here as a clear sign that my numbers are correct, but as opposed to Republicans and Democrats. Over here, you can't be both. Over here, you could be Republican, or you could be female, or you could be both Republican or female. There's a possibility of overlap here in the process. Why is this important? Well, if I want to compute the probability of Republican or Democrat, that would equal the probability of Republican plus the probability of Democrat. That's how and this is a logical OR, which means that the likelihood I'll get one of the two of these things, because there are other possibilities here in the larger event space here. There are people who don't register as either Republicans or Democrats. So this would probably be most people, but it may not be all of them in the process. This one over here, however, with non-exclusive events, the formula is different. The probability of Republican or female would be equal to the probability of Republican plus the probability of female minus the probability of Republican and female. Oops, let me go back here. In parentheses, Republican and female. Now, why is that true? Why are they different in this thing? And part of the reason they're different is because there's overlap. If I'm doing this formula here, I count everybody that's in the Republican circle, and then I count everybody who's in the female circle. But there's this group in here that I'm counting both times. I'm counting them when I count Republicans, and I'm counting them when I count females. So I subtract it once. The Republican, when they have, and this is the difference between exclusive and non-exclusive events. And one of the things I'm going to ask you this week is, you provide me with examples of things that are exclusive and non-exclusive events. I'm asking you to think through what those things are. Now, you may have noticed here that one of the things I did is, okay, Steve, you said probability of Republican and female. You haven't shown us that one before. There is another formula here. Probability of A and B is equal to the probability of A times the probability of B. Now that's up here I'm saying the probabilities. This is an OR probability. This is an OR probability. This is an AND probability, which means that that fits both criteria. Now the probability of a Republican and Democrat it's got to be 0 because you can't have both things at the same time. There's no overlap in here in this process. Over here, however, is different. If, say, the probability of being Republican, let's say, is 0.4. I don't know whether that's true or not, but we'll say it. And the probability of being female is 0.6. Then the probability of Republican females would be 0.4 times 0.6 or 0.24. In this case, there is a point here because probabilities are always less than 1 and they're always greater than 0, or less than or equal to 1 or less greater than or equal to 0. You can't have a negative probability. You can't have a probability of greater than 1. Probability of 1 means that something's certain to happen. This stuff is in the text for this week. Let me sort of take this issue back a little bit further. I'm kind of going, so suppose, oops, so I have 4 marbles. Let me do 5 marbles actually. I have 1 white and 4 blue. What's the probability of a blue marble? Denominator's 5, because there's 5 marbles altogether. 4 of them are blue, so the probability of a blue marble is 4 out of 5. 4 divided by 5, or 80%. That's the likelihood. There are 8 chances out of 100, 8 chances out of 10 that I'll get a blue marble. I reach in here and I pull out one, and oops, I got the white marble. So there's a 20% chance of it, you know, and I still have 4 blue marbles here. Let me go back again and say, what's the chance if I would pull 2 blue marbles? Well, first of all, I pull a blue marble, and the chance of that first one is 80%. However, what happens, what about now? Once I've taken that out, the real key question is, do I take that blue marble and I put it back, or do I keep it out? If the blue marble goes back into here, then the 2 events, drawing 1 and drawing 2, are independent of each other. What happens in drawing 2 doesn't depend on what comes up in drawing 1. If I don't put it back, then the second drawing is dependent on what happens in the first drawing. If my first drawing, I get a white marble, then the probability of getting 2 blue marbles is 0 because it's not going to happen from that thing. However, if I've taken the blue marble out and I have 4 marbles left, the probability of a blue marble on the second draw is not 80% anymore, and now it's 75% on this time around, because there's 3 blue marbles out of 4 possibilities. That becomes a really important, that concept of independent and dependent events is a very important one. We tend to do, human thinking is such that it's like if you've gotten 6 heads in a row flipping coins, we all believe it's like, oh, either he's on a streak, so he's really likely to get a 7th one, or odds are against him, you know, because you just can't go that long with keep getting all our heads. But the truth is, on the next draw, the next flip of the coin, if you've flown 6 heads in a row, on the next one, the odds are exactly 50% again. They're the same as they were before because the events are independent of each other. When I have these 4 marbles left and I have pulled one out, pulling this one out of the thing makes the second event dependent on what happened in the first one. So I'm going to ask you to come up with examples for that also this week. To think through, it's like your words, your examples of this. What are independent events and dependent events? Because that makes a difference in how you compute different kinds of things. I think about lotteries, for instance. With a lottery, it's like drawing marbles here. It's like, what's the odds of getting the winning ticket? Well, because the numbers are so big, it makes very little difference whether one's been pulled out before it or not. But it's in some cases, it makes a lot of difference, and you need to be thinking about that as we do computations and things. The other crucial issue from this week is the concepts of permutations versus combinations. And let me do some definition of that first of all. A combination is let me do a horse race, for instance. Suppose you have 10 horses and you want to pick 3 winners out. You want to pick the 3 winners. You don't care what order they come in, but you want to pick the top 3 coming in. There's a formula for that, and it looks like this. This sub n c sub r, the number of combinations of 10 things taken 3 at a time. 10 horses taken 3 at a time. Well, how many possibilities are there for that? And it gives you this formula here. This is, it's equal to n factorial divided by n minus r factorial multiplied by r factorial. This is what that looks like. If you've been a while since you've done your mathematics and played with algebra, what this means is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by n minus r. That's 10 minus 3 quantity factorial. I'll talk about that in a little bit here. Times 3 factorial. Well, leaving this much the same. That would be 7 times 6 times 5 times 4 times 3 times 2 times 1 times three times 2 times 1. That's a pretty complex formula. It's complex in the sense that it's a lot of multiplying to do to get a right answer. And I'll tell you the good news is, I'll take you to Excel here in a second, show you. It's like Excel do that for you and just bang, it's done. That's how many combinations there are of possibilities of 3 winners among 10. Now, permutation, which is different than that, is doing the same sort of thing, but this time it's done in the how many of those things come up in order? That is, up here, I might say one combination is horse number 1, horse number 2, and horse number 3. But what would fit here is also horse number 3 plus horse number 2 plus horse number 1, or horse number 2, horse number 3, horse number 1. Those are all different combinations. When I divide down here, I'm sort of getting rid of those things. What this thing here says is, to be picked in a permutation, I'm talking about horse number 1 first, horse number 2 second, horse number 3 third. If I'm talking about horse number 3 first and horse number 2 second and horse number 1 third, that's a different permutation. Those are different things. Sometimes the order is really important, sometimes it's not. You think about um, if you're working with ordinal numbers, then the permutation becomes really important because the ordinal stuff really makes a difference. If you're just talking about who happens to fall where, it's not very important. It's a combination instead. The mathematics here, I mean, really it's the arithmetic here, is really complex. It just takes a lot of time. And personally, I hate that kind of stuff. However, the good news is, come on, Excel has a formula here. That's not here. The formula is here. Comben, in order to of C4, 5 things taken 2 at a time. And the number is, it comes to 10, there's 10 combinations that are possible. There's also a formula here, equals permut, and again, I said C4 divided by, 5 things taken 2 at a time, exact permutations. There are twice as many permutations here as there are combinations. These formulas, come on, Comben. Now, part of the reason I put in here cell values rather than actual values is because I can go back and change this thing and say, suppose, how would the combinations change if I have 10 combinations as opposed to 5? Well, suddenly it jumps from 10 to 45. How about if I had the taken 3 at a time rather than taken 2 at a time? The numbers jump again. The bigger these numbers get over here, the more these numbers here jump. And the difference between combinations and permutations jumps even faster. It gets bigger as these numbers here go up. I don't know that aside from when I first had to do it in my math class back when I was an undergraduate, I never figure combinations and permutations out by hand anymore. It's just too much energy. It's a waste of time. I don't want to do it. But I'm going to ask you to do some of that this week and just start to figure out combinations and permutations. Key concepts this week is I want you to be able to figure out a fundamental counting rule, so you can figure out how many possibilities there are for things. I want you to get a sense of, I want you to get examples in your head about exclusive and non-exclusive events. And then ultimately what I'd like you to do is actually find some figures and probabilities when you have of A and B or A or B, and figure out that under the different kind of scenarios. That will get you through the week. Next week it gets a little more complex. So one of the things that we're talking about here, if you haven't thought about it, is all these things are discrete numbers. How many horses can finish? You can't have 2.5 horses and finish in the first 3. It's like there's specific numbers of things here. Well, next week, and weeks coming up, we'll get into some different kinds of numbers with it. But those are the concepts that are really important in this chapter to begin with. Nothing new here.